Okay then, so now let's just look at an example using the football data we looked at in the previous chapter. Okay, so this is the league table from the 2019-2020 Premier League season. And what we're going to do here is, rather than do analysis of the table all at the same time, we're going to split it and suppose that we're given X variables that are just the wins and draws, and the Y variables that are just the goals for and the goals against. Okay. Now, the reason we're not including the losses and the goal differences here is that we know that if you know the losses, the wins and draws, if you know the wins and draws, the losses are determined. Similarly, if you know the goals for and the goals against, the goals difference is determined, and that would lead to non-singular covariance matrices, which we want to avoid. So, although the R packages will deal with that just fine, the way we presented the material in the notes, we assume those vectors were invertible. So the questions we're going to consider are things like, how strongly are the match outcomes, so wins and draws, with the goals for and the goals against? And what linear combinations of the wins and draws is most strongly correlated with what combination of the goals for and goals against? So the way we start off doing CCA is to compute our three covariance matrices that we need. So if I let my X variables be this wins and draws columns, and my Y variables be the goals for and the goals against columns, and I can work out the covariance matrix of the X's by CovX, covariance matrix of the Y's by CovY, and the cross covariance CovXY. And that gives us these three matrices here. Now, the first thing we need to do before doing CCA is to work out this matrix Q. Okay. So Q was the inverse square root of SSX times SXY times the inverse square root of SYY. Okay. So to do that, we need to find the inverse square root of SXX. So one way of doing that is via the eigen decomposition, or the spectral decomposition. So if we work out the spectral decomposition, we use this command eigen in R. That gives us the eigenvectors, which we put into the columns Q here. The eigenvalues, which we're going to call lambda, the diagonal matrix here, and then Q transposed. So one way to work out the square root of the matrix is then just to square root these eigenvalues. And the inverse square root is 1 over the square root of those eigenvalues. So we can work out SXX inverse square root quite easily here by taking the eigenvectors we found times by the diagonal matrix of 1 over the square root of the eigenvalues times the eigenvectors transposed. Okay, and that gives us this matrix here. Similarly, we can do the same thing for SYY to get the inverse square root of that matrix. If we put all this together, it gives us our Q matrix, which is given by this matrix just here. So what the theorem says that we looked at was that the first canonical correspondence vectors are given by the left and right singular vectors of Q. So if we work out the singular value decomposition of Q, we get expression 5.8 here. So this is the first left singular vector. This is the first right singular vector. This is the second left singular vector, second right singular vector. This is the first singular value, the second singular value. So let's look at the singular values. The first one is 0.955, so close to 1. So the first correlation coefficient is 0.955. And the weight vectors, as I said, are the left and right singular vectors times by the inverse square root of the covariance matrix C. So A1, the first singular vector for the x's, is given by this expression. It works out to be minus 0.17 and minus 0.10. Similarly, for the first CC vector for the y's, we get this vector here. So once you've got the singular, the CC vectors, we can work out the canonical correspondence variables. Okay. So the first CC variable is going to be A1 times our x's, or A1 transpose times our x's. So we're going to get minus 0.175 times the number of wins. These are centered, of course, so we've subtracted the average number of wins here. Minus 0.104 times the number of draws, centered draws. So if we think about trying to interpret what this is something like the negative of the number of points scored. So normally in football, you get 3 points for a win and 2 points for a draw. Well, here you're getting something like minus 2 points for a win, minus 1 point for a draw. Okay. So eta 1 is measuring something to do with the overall performance, weighting the wins to the draws. Psi 1 is saying it is 0.02 times the number of goals, minus that, plus 0.05 times the number of goals conceded. So there's a ratio of about 2 to 1 here. So goals conceded are more important than goals against, it's saying here, in terms of correlating with this measure of performance that weights the wins and draws. Yeah, there's not a 1-to-1 weighting. Goals against are given as more important here than goals for. Okay, so in R, if we work out how to do this, if we work out these transform variables, well, first thing we need to do is remove the column means. So I've used that sweep command again, or you can use the centering matrix, whatever you like, to get a centered version of my x's and my y's. And then all I've done to work out the etas and psi is just multiplied those matrices by the two vectors I found, A1 and B1. And that gives me this list of variables, eta and psi, the first canonical correlation variables for each data point. So one thing we might often do is sometimes plot these. So let's have a look at a plot of them. So we've got eta here along the x-axis and psi along the y-axis. Remember, eta tells us something about the number of points. So it was 2 times the number of wins plus 1 times the number of draws, or the negative of that. So you can see that Liverpool, who won the league, have the largest negative value here, and Norwich, who were relegated first, have the largest negative value, the largest positive value. Let's go. And similarly for psi. So we can see here that, remember that goals conceded were weighted more than goals against. So we can see that Liverpool and Manchester City stand out as they scored a lot, but conceded very few. So we've got a large negative weighting here. Whereas Norwich conceded a lot, but scored relatively few. Okay, so Norwich have a large value of psi here. Okay. So that is how we do CCA ourselves. But in practice, of course, we don't want to go through all this every time, working out all these matrices. Thankfully, there's an R command that does all the work for us. So you have to load a package to do this. So if you've not installed it, you have to install it first time you use it. Install.packages, CCA in quotation marks. Okay. But once you've got it installed, doing CCA is really easy. It's just CC of X and Y. Okay, and this returns a list. If you look at the various elements of the list, you should be able to find all the numbers we computed above. So the canonical correlations are given by the element core here. So we found the singular values to be 0.955 and 0.705. And that's what we found before, 0.955, 0.705. Then we can also find the canonical correspondence vectors. So we've got the first vector here with minus 0.175 and minus 0.104. And this is the second vector for the x's, which we've not talked about yet. And here then are the first vector for the y's, minus 0.023 and 0.054. Okay, vector 1, vector 2, A1, B1. And finally, we can get the CC variables, the canonical correlation variables, transformed variables, So for the x's, it's this first column here. So the first value is minus 0.243. That's what we found here, minus 0.243. And for the y, the first value, that's this column here, was minus 0.18. That's exactly what we found before, minus 0.18. And we can also look at the later components as well. So if you looked at the second singular value, we found that was 0.705. And if you look at the second set of CC vectors, we found A2 to be 0.031 and 0.329, and B2 to be this value here. Okay, so go back and check that in the notes. And that gives us the second pair of transformed variables. E2 is going to be 0.03 times the number of wins, 0.329 times the number of draws, and similarly for Psi2. Okay. So if we think about what E2 is, this is measuring something just like the number of draws. Yeah, essentially ignoring the wins, just working out the number of draws. And similarly, Psi2 is close to the total number of goals in a team's game, or the negative of that.